Section 15.7, the divergence theorem. Now for us, this is going to be a fairly short section, so I'm going to dive right in, give you the divergence theorem itself. So here we have a solid region Q. So let Q be a solid region bounded by a closed, has to be closed, surface S oriented by a unit normal vector in, okay, directed outward from Q. Okay, so just to give you an idea of what we're looking at here, I've got some closed surface, so maybe, you know, something like this, I don't know. But whatever it is, it's closed, so I'm saying I'm closed on the bottom here, and it's a closed surface S, and then I've got my interior region Q here. Then S is oriented such that our normal vector is always pointing away from Q, pointing outside of Q. Okay? So that's what we're getting at there. All right, then, if f of xyz, this is a vector field, m I direction is equal to m in the I direction plus n in the j direction plus p in the k direction, is a vector field such that m, n, and p have continuous first partials, such that m, n, and p have continuous first partial derivatives on Q. Then our double integral over S of f dotted with n ds, the flux, right? It's the same thing for the flux, that's equal to the triple integral over Q of the divergence of f dv. Okay? So remember, the divergence of f is equal to the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. Okay. All right, so why don't we jump right in with an example here. So let's evaluate double integral over S of f dotted with n ds, where f is equal to xy in the I minus 1/2 y squared in the j plus z in the k directions. Okay, and the surface is given by the following. Okay, so we've got z equal to 4 minus 3x squared minus 3y squared for 1 less than or equal to z less than or equal to 4. X squared plus y squared equal to 1 for 0 less than z less than 1. And z equal to 0. Okay, so our surface is going to be formed by this. So our region Q is what's bounded by these surfaces. Okay, so we're going to want to sketch this, and this is kind of what I sketched earlier, but let's go ahead and sketch it. So we have got x, y, z. Okay, so 4 minus 3x squared minus 3y squared. Those, this is going to be a paraboloid, right, opening down. So this is going to be coming down, see, from z is 1 to 4. So 1, 2, 3, 4. Okay, so in the xz plane, that trace here is just going to be 4 minus 3x squared. So 4 minus 3x squared. So at 0, of course, that's going to give us 4. Pick a color for this first piece. Okay, at, let's see here, x equal to 1, that's going to give us 1. Okay, and that'll be the same way in the opposite direction for x as well, because it's getting squared. Okay. And it's going to be the same for in the y direction because it's minus 3y squared as well. So let's see, it looks like it's going to be like this, okay? And then coming in the y direction, it's the same thing. So we're going to have this point, we're going to have 1, 1, negative 1, 1. There we go. Okay. So it's going to kind of look like this. So this is the one that we're looking straight at the side, and then the back comes down like this and this, and we've got our bottom of this portion of our curve right here. Let's see if I can do a little bit better than that. Not much, but a little bit. Okay, there we go. All right, and from 0 to 1, we have x squared plus y squared. So that's just going to be a cylinder. So that's going to come straight down. So 0, so we've got the point 0, negative 1, 0, 0, 1, 0, 1, 0, 0, negative 1, 0, 0. So that's just going to come straight down and create this cylinder here. Okay. So hopefully you can kind of see what's happening here. We've got kind of this bottom half is like a cylinder, an actual bit of cylinder here. So like a bell top on top of a cylinder. And then the bottom is solid because it's going to be z equal to 0. That's just the xy plane. Okay, so there we have it. Looks kind of like a little bird cage that becomes straight here at the bottom. Okay, there we go. And of course it's solid on the very bottom. Whew. Okay, so it is a closed surface. It is a closed surface, and we do have our bounded region Q within. So according to the divergence theorem, our integral over S of f dotted within ds is equal to the triple integral over Q of the divergence of f dv. All right, so we need to know, well, what is the divergence of f here? So that's going to be, where's f? It's up here somewhere. There it is. So here's f, right here. So the divergence of f is going to be the partial of m, which is xy with respect to x, so that's just going to be y, plus the partial of n with respect to y, that's going to be negative 1y. Then the partial of the last part here with respect to z is equal to 1. So the divergence of f is y minus y plus 1, which is nice for us because that's just equal to 1. Yeah, positive, that's a plus. There we go. Equal to positive 1. Okay, so our integral then is going to be equal to the triple integral over Q of 1 dv. So that's dv is dz, dy, dx, and we need to find out what our boundaries are on each of those. So in the z direction, we are bounded by z equal to 0 and z equal to 4 minus, what was it, 3x squared minus 3y squared. Okay. So I'll put those boundaries in on z. So that's going to be 0 to 4 minus 3x squared minus 3y squared. Then y is going to be bounded by this circle here. Grab my other color, this circle here. So if I look at that in the xy plane, this is a circle of radius 1. So that's x squared plus y squared is equal to 1. So our lower boundary is y equal to the square root, negative square root of 1 minus x squared, and our upper boundary is going to be y equal to the positive square root of 1 minus x squared. Okay, so we can put that in. So that's going to be negative square root of 1 minus x squared to the positive square root of 1 minus x squared. And then x is just going from negative 1 to 1. So grab a third color, negative 1 to 1. So here you can see that x is going from negative 1 to 1. Okay, so that looks like an absolute hot mess, but it also looks like a great opportunity for us to convert to polar coordinates. So let's go ahead and do that, remind ourselves how. So let's rewrite in polar coordinates, just convert. Woo! Too far, too far. So convert to polar coordinates. This is not absolutely necessary, but it's going to make our lives a whole lot easier, and it's set up beautifully for it. So let's go ahead and do that. So our boundaries then are going to become r dz dr d theta. Okay. Our integrand is still just 1, right? And then our integral on z is still the same, except in polar coordinates. That's going to be 0 to 4 minus 3 times r squared. Okay. Then r is going from 0 to 1, and theta is 0 to 2 pi. So this will be a much, much easier thing for us to integrate. So let's go ahead and do that. So that's going to be equal to the integral from 0 to 2 pi of the integral from 0 to 1 of rz evaluated from 0 to 4 minus 3r squared dr d theta. So that's the integral from 0 to 2 pi, integral from 0 to 1 of r times 4 minus 3r squared minus 0 dr d theta. Distribute to simplify. Integral from 0 to 2 pi, integral from 0 to 1 of 4r minus 3r cubed dr d theta. Integrate. So from 0 to 2 pi of 2r squared minus 3/4 r cubed, evaluated from 0 to 1, dr d, we already did dr d theta. Evaluating at 1, we get 2 minus 3/4 at 0 at 0. So this is the integral from 0 to 2 pi of 2 minus 3/4 d theta. 2 minus 3/4 is going to be 8 minus 3 is 5, so 5/4 d theta. So that's equal to 5/4, getting ahead of myself, theta evaluated from 0 to 2 pi. So that's just equal to 5 pi over 2. So there we go. So Stokes' theorem is kind of our third dimension equivalent to the surface integrals, right? We're kind of taking that up a notch and putting it into the third dimension with the triple integral. Okay, so hopefully that's pretty straightforward. As always, though, if you do have questions, please let me know. Be happy to answer anything you've got. But this is a nice short one. And next on the docket is 15.8, the last section, and that's Stokes' theorem.